Well, good evening, AP Physics students. Mr. Kurse coming at you here with some hints for you on problem 18 out of chapter 13. And this is an interesting one. We've been talking about linear expansion. Things heat up and they get longer and wider. So here's the problem. The problem says if I have an object of length L and width W, what if the whole thing heats up, right? And if it heats up, it might grow by, say, delta W, and it might grow by delta L in this dimension, okay? Well, if that was the case, what would be an expression for the change in area of this object? So we talked about coefficients of linear expansion, but how would it affect area? So here's some hints to get you going on this problem. First of all, remember here that the area, the original area here is just A, which is WL, right? Length times width is the area of this block. Well, after this thing heats up, it would have area A plus delta A, right? So the area of this whole thing would be A plus delta A. Well, what would that area be? Well, it would be W plus delta W times L plus delta L. Okay? So, in other words, the area of this whole thing. So, this in here would be delta A, all of this area in here. Okay? And now the problem asks us to show that delta A in the end, delta A should equal 2 alpha L W delta T, right? And it does also tell us that you can use in your proof, you can eliminate very small areas, okay? Very small areas. So let's see if we can decipher what this means. Okay. Well, let's use a little good old-fashioned algebra here and FOIL this out. So A plus delta A must equal WL plus W times delta L, right? Plus delta W times L plus delta W times delta L. Now, in the world of physics here, if you have a very, very small quantity times a very, very small quantity, that quantity itself is very, very small. So what the hint the problem gives us here is this is something that can probably be neglected. So let's get rid of that. Furthermore, in this equation, if A is equal to W times L originally, we can subtract that from both sides of the equation and get that delta A then, so if I subtract this from this, delta A, right, because this would cancel out, would just be W times delta L plus delta W times L. So that would be the change in area of this rectangular object. Now we're not quite to here. So let's see if we can't carry this out a little more. Remember here that in general our formula is delta L is equal to alpha times L naught times delta T. And this would apply both to the width and to the length. Okay? So I think it would be pretty reasonable for us to say delta L is equal to alpha L delta T, right? And so that's this delta L here. And similarly, delta W would be equal to alpha W delta T, right? So this length expands and this width expands, and those equations would be those equations. So if we then combine this equation, in other words, take this and plug it in here for delta L, and then take this and plug it in for delta W, we should get the following, right? So I'm plugging this in there, listen there, and I'm going to get delta A is equal to W times alpha times L times delta T plus, let's see, hopefully I don't run out of room here, alpha times W times delta T times L. Well, notice here that this is really, these two expressions are the same. I've got a W, an alpha, a delta T, and an L in there. So that's really just 2 alpha L W delta T, which is what we set out to show. Okay? So there we go. Neat little proof, almost mathematical in nature, showing that with our formula for length, you can actually, if you neglect very small areas, you can actually get a formula for area. And I'm going to leave it to you as an exercise to show that for most materials that beta, the expansion of volume expansion, is actually equal to 3 alpha for the same material. So you could do a similar derivation in 3 dimensions that would work for that. All right, nice work, physics students. For your thought of the day today, is there life elsewhere in our solar system? As it turns out, for many years we've thought that one of Jupiter's largest moons, Europa, could have life on it, even though it's frozen and irradiated and desolate. So anyway, super interesting article. If you're interested in learning more about some of the Jupiter's moons and some of the unique features and what, if any of them, could support life, see Mr. Kirsten. I'll have this article with me all week. All right, nice work, physics students. We'll see you tomorrow.